Welcome back, everybody. Glad you could join us. Last one from the news roundup so far for this week. Webb looks at the infrared. Need to just kind of change some of this. I don't like this in small letters as I was typing it, so we'll just make that correction really quick. So Webb looks at the infrared, to the central engine of the Circinus Galaxy. We're focusing in this post about the James Webb Space Telescope milestone. It's a deep infrared look into the central region of the Circinus Galaxy, a nearby active galaxy about 13 million light years away. It's not just another image release, which you can see if you go over to Patreon, to my Easy Astronomy site. I have the image there of it. It's a new way to see how matter feeds a supermassive black hole. Circinus is classified as a Type 2 Seyfert galaxy, meaning it harbors a supermassive black hole that's actively accreting material, and it's cloaked in a dense dust that absorbs and re-radiates starlight. That dusty environment makes it extremely difficult to see what's really happening at the core using visible light telescopes alone, until Webb came on the scene. Webb's near-infrared imager and slitless spectrograph, NIRISS, equipped with a special tool called the aperture masking inframeter, acted like an array of smaller telescopes working together. This trick dramatically sharpened Webb's view, effectively doubling its resolution over the central region. That's like turning Webb into a 13-meter telescope for this specific site, all while in space, unobstructed by Earth's atmosphere. So what did Webb reveal in this? For decades, astronomers debated whether the bright infrared emissions near active black holes, where they came from. Did they mostly originate in the outflows, streams of superheated material blasting outward from the black hole, okay, or from dust that was already pulled inward toward the black hole? Webb's new data suggests the answer leans heavily toward infalling material. Roughly 80% of the infrared glow in Circinus comes from the hot dust very close to the black hole's center, inside the dusty torus feeding it. Less than 1% comes from the outflows that were once assumed to be the prime culprit. This big shift in our understanding, it's huge. Previous models struggled because ground-based telescopes and earlier space telescopes didn't have the resolution or the infrared sensitivity to tease apart the different components. Webb, though, can peer through that dusty veil and isolate the infrared signatures from specific regions. That's what makes this not just a pretty image, but a scientific milestone. Now that astronomers know how this technique works, using interferometric imaging in space to separate accretion regions from outflows, it can be applied to other nearby black holes. The goal is to build a statistical sample, dozens of galactic cores observed this way, so we can understand whether Circinus is typical or unusual. To bring this back home, when we look up on a clear night and think about the silent dance of galaxies out there, especially as we begin to move out of winter into spring, but in winter, Cetus has tons of galaxies to look at. We're seeing the tip of the iceberg. Instruments like Webb's NIRISS are revealing the powerful hidden physics that drive galaxy evolution, from feeding black holes to shaping the light we eventually receive here on Earth. And every time Webb pushes those boundaries like this, our mental map of the universe gets just a little bit more detailed, becomes just a little bit more clear, and that's a wonderful thing as our knowledge expands. Thanks for tuning in. Stay curious, and of course, clear skies, keep looking up. Talk to you next time.